Okay, so balancing is super important, obviously, because we cannot create matter from nothing. That's like the one of the fundamental principles of life on Earth, unfortunately. And so, people who wanted to make gold from lead by mixing acid with it, that just was not going to happen. And what we're going to do next again is switch to more of the quantitative side of chemistry. And we need these balanced equations in order to figure out ratios. Okay? So you're basically, all you're doing is finding the same, making sure there's the same number and type of atoms on both sides of the arrow. And then again, depending on who your grade 10 teacher was, you must make sure that your coefficients, or the big numbers out front, are reduced. You can't have 2, 4, 6, 10. You're going to lose marks, okay? And I believe some of the grade 10 teachers sort of let that slide. You have to make sure that you have the most reduced, because that's really what would happen. In a chemical reactions, atoms and molecules and compounds would not waste materials. Okay, so the law of conservation of mass, matter cannot be created or destroyed. So you have to have the same number and the same type on both sides of the chemical equation. So we'll just review a little bit about how to count atoms. So we already talked about this. This is similar to math. If there's nothing written here, then a 1 is understood. We'll look at a shortcut where you can actually count the polyatomic ion, like as the polyatomic ion, especially in displacement, but we'll get to that later. So then this one, when you have a 2 outside of the brackets, so again, when you have a polyatomic ion, that's why the brackets are so vital, because that means that there are 2 oxygens and 2 hydrogens. Again, sort of similar to the exponent laws in math, where if it's outside the bracket, you multiply. But there's only 1 calcium because it is not a part of the brackets. So the brackets there around that hydroxide are vital. And then the last one with the coefficient out front here, this applies to the calcium and to inside the brackets, so you have to do both of them multiplying. So there are 3 calciums, and then 3 times 2, 6 oxygens, 3 times 2, 6 hydrogens. Okay, so let's take a look at this last one. So the big number out front is called a coefficient. These are the numbers that you're going to change when you balance. The little number comes from the formula. We already talked about subscripts. Can't change those. Okay, so the subscript comes from writing the formula. That's why it's so important to be able to write the formula, because then if you can't write the formula, then you won't be able to balance, and then you'll come to me and say, Ms. Todd, I can't balance this, and then it's so sad for me, and I have to say, go sit down. Okay, so the next slide has hints about, or tips maybe that you can use, but I really don't care what you do, okay? So you can make what I call like a left side, right side chart, or reactants and products, count out the number of atoms. I know that Mr. Vine does something underneath, some wacky thing. You do whatever makes sense to you. Really, like I said, technically, you can even do it by inspection. So we're going to do 4 examples, and I'll try a different strategy each time, just so you can see how it's going to work. What I like to do, especially when it's displacement, which is a very common type of reaction in grade 11 and 12, is if you have an odd number for something, then I try to make that even first, because then it's a little bit easier to balance. Most people like to leave hydrogen and oxygen last and balance everything else first, because you might notice that they tend to balance themselves out. Whatever you choose to do, make sure you check when you're done, okay? Just take a quick check, 5 coppers on this side, 5 on this side, whatever, okay? And again, also checking that your coefficients are reduced or the most simplest. Again, I'm not sure that the grade 10 teachers focus on that, but we really need it. It really does matter. Okay. So this first example has a single displacement, aluminum plus copper 2 chloride makes aluminum chloride plus copper. So the copper here and the aluminum here are by themselves. So that makes your life easy, because you can put whatever you want in front of them and it doesn't influence the compound, right? So maybe you want to focus on those last. Again, my eyes are sort of drawn to this, that this this chlorine here is a 3, and here that's a 2. So the chlorine on the product side is odd, and on the reactant side is even, okay? So again, you can make a chart if you want, do the thing underneath, whatever works for you, okay? So on the left side, right side, or the reactants and the products, So we have 1 and 1, 1 and 1, 2, 3. So again, my eyes are drawn to the 2 and the 3. That's going to be a problem. Okay, we need it to be reduced. We need it to be even. You're never going to be able to balance it otherwise. Having the most reduced does not necessarily mean fractions. You do not need to use fractions. If you want to, that's fine, but you don't have to. I know, again, depending on who your grade 10 teacher was, maybe that was a focus, but you don't need to do that. Okay, so we can still do most reduced without using fractions. So here, I don't like this. I'm going to make it even. The easiest way to make it even, or the most reduced way, is to multiply by 2. Sorry, I had to sneak that in there. So that changes this and this. I don't really care about the aluminum because it's by itself over here. I'm going to fix that at the end. I'm going to go fix this. So when you have something like this, like single displacement, it's easy. You can just put 2. You can put whatever you want. I'm going to put a 3 here. Done. So we have, always check, 2 aluminum, 2 aluminum. 3 coppers, 3 coppers. 3 times 2, 6 chlorines. 2 times 3, 6 chlorines. Okay? None of them, 2, 3, 2, 3, cannot all be divided by the same thing evenly, so we're done. Yes? Yes, now, to be honest, Mr. Vine always shows me and I'm like, what? So you do whatever makes sense to you. This one says simple-ish because you do have to remember here we have magnesium, burns in oxygen, but what's the formula for oxygen? Jacob. Good. O2. It is diatomic. So if you have to write it from words, that can be tricky, okay? And then magnesium oxide. So again, you have to, I feel like I did this one a zillion times, but you have to crisscross. But then also, it's ionic, so you have to reduce, okay? So this is one that you can do probably by inspection. This is one where you can use a fraction, but you don't need to. So here we have 2. We need 2 over here, which means we need a 2 there. Done. You can make your chart, you can make columns, you can do whatever you want. So you could, some of you might have written this. That's fine too, but it's not an expectation. You do not need to use fractions, okay? This is still reduced. 2, 1, 2, okay? Just like before, like if you write the 1 in here, that's fine, I won't take marks off, but you don't have to, okay? So it's sort of understood. It's not 0, it's 1, okay? Okay, so this next one is double displacement. So when you do double displacement or single displacement, polyatomic ions are going to stay together. So then you can make it super easy to balance because really you're going to have very few possible numbers, 2s or 3s or 1s, based on the charges. Maybe if you had a weird transition metal, you might have 4 or 6, but normally you're just going to have 2, 3, or 1. Those are the charges, right? So, and the polyatomic ion is going to stay together. This is nitrate, so is this, right? So you can count the nitrates together. You don't have to count nitrogen and oxygen separately. So ATE, that's nitrate on the back of the periodic table, right? And then lead, so the 2 crosses all the way across. And then IDE, that just means iodide. Potassium is 1 as well, so you get Ki. When you do double displacement, all you're going to do now is switch. So in grade 10, your teacher probably talked about this terrible analogy of dancing partners and the girl switch or the boy switch, right? They love that. So this K, or the positive, is now going to go with this negative, and this positive is going to go with this negative. So you don't really have to try to look up what these are again if you've done it here. So if you're the kind of person who likes to show lots of work, then you can streamline your process, because in displacement, all you're doing is switching partners, okay? And we'll review the types tomorrow, but that can help you when you're writing reactions. So now this lead with 2 is going to go with this iodide, which is 1, to make lead 2 iodide. And this K is going to go, which is 1, with the nitrate. So you decide, they're both 1s, if you want brackets or not. It doesn't matter. Okay? So when you do this kind, it's like, oh my goodness, there's so many things, there's so many letters, and what I recommend that you do is look at this together. How many leads? 1, done. Nitrates, 2, 1, put a 2. K's, 1, 2, put a 2. I's, 2, oh, made it work. So double and single displacement should be the fastest ones. Most of the time, to be honest, they're already going to be balanced, okay? But you can't, the columns, like the number of charges you can have, are really just like 1, 2, 3, right? Or 3, 2, 1. So there isn't a lot of variety. But you can make a chart every time. You can count all the atoms every time. Whatever is going to work for you, okay? So this one, it says it's the most annoying. This is complete combustion. So we're going to review that tomorrow. So here we have carbon dioxide and water. So the reason that it's the most annoying is because there is oxygen on both of these. And because it's O, oxygen is diatomic, it has to have a 2. So that makes it even, right? Sometimes in the fuel for hydrocarbon combustion, you can also have, could be like an alcohol, which has oxygen in it as well. So there's a little bit of variety here. These ones, usually students find the most annoying to balance, okay? So whatever makes sense to you. So we have 2 carbons and 1, 6 hydrogens and 2, and then oxygens we have 2, and then we have 2 plus 1. These ones are the most annoying because there is like no rhyme or reason sometimes. So it's tempting. Most people would want to put a 2 here first, right? But then that would mean 6 hydrogens. Like that would balance the carbons. So to do 6, you would have to put a 3 here, which you're going to get 3 then, and that's never going to work here, right? So, you know, using trial and error, you can use fractions, but again, most people don't like to do that. As an aside, if there's an even number of carbons here, you're probably going to multiply by 2, okay? Because that's going to make this 12 hydrogens, which we can then put a 6 here, which is also even. But you can go, like you could have tried this, right? And then you would have gone to balance the hydrogens and then realized, oh, I can't do that. That's not going to work. Okay, so it's trial and error too. Get your science sword, your pencil, okay? So then we're going to put a 4 here. That makes 12 hydrogen. So to make 12 on the other side, I need a 6. And then we have 8 and 6, which is 14. So now we have an even number. So what can I put here? Now again, depending on who your grade 10 teacher was, you can do this as well. You can divide everything by 2. This is an acceptable answer, but you do not need to use fractions. You don't. So if you don't like this, don't even write it down, okay? Just do this one. Check at the end. 2, 7, 4, 6 cannot all be nicely divided by 2. 4 carbons, 4 carbons. 12 hydrogens, 12 hydrogens. 14 oxygens. 4 times 2 is 8 plus 6 is 14. If you don't like mental math, then don't use a calculator. I will never stand up here and be like, ugh, why aren't they using mental math? No. Don't make annoying, simple mistakes, okay? You'll get frustrated with yourself, ruin your confidence, screwing yourself up, okay? So now you have a choice. So you can continue